Okay, so you've seen it, right? AI can create these absolutely stunning pieces of art. It can write code that would take me weeks. And yet, it still struggles with the most basic common sense. That right there, that's the AGI paradox. In this explainer, we're going to dive deep into this gap between what AI can do and what it can't understand. And we're going to explore why building a true thinking machine is so much more complicated than just making our current models bigger and bigger.
So let's just start with this core idea right here. On one hand, you've got AI that can write poetry that genuinely feels human. But on the other hand, it has no clue what it's actually talking about. It's got all this capability, but zero real comprehension. And that is the central puzzle we're digging into today. What's the missing piece that's stopping these incredible tools from becoming true minds?
All right, so what are we actually building here? To really get to the bottom of this paradox, we've got to be super precise with our language. You hear the terms AI and AGI thrown around all the time, but honestly, they mean vastly different things. And understanding that difference, well, that's the key to seeing where we are today and where we're really trying to go.
Let's start with the big one, the definition of intelligence itself. Now look at this slide. It's not about having every single answer stored away somewhere. Real intelligence is about what you do when you don't have all the information. It's the ability to adapt, to learn, to solve brand new problems on the fly. And that is such a critical distinction when we start talking about what today's AI can, and more importantly, cannot do.
Okay, this table here, this is really interesting because it maps out the whole journey. We started way back with narrow AI, or ANI. Think of an app that does one thing really, really well, like, say, playing chess. Today, we're in the age of broad AI, or API. These are the models like GPT-4 that can do a whole bunch of different things. But now, look at that last column, for AGI. It needs universal scope, causal reasoning, true autonomy. That's not just the next step. It's a massive, massive architectural leap. So the real takeaway is that what we have now, this broad AI, it's incredibly powerful, but it is fundamentally a different beast than the autonomous, reasoning AGI we're all aiming for.
So this brings us right to the dominant belief in AI today, what's called the scaling hypothesis. The basic idea is, hey, if we just keep making our current models bigger, feed them more data, throw more computing power at them, eventually true general intelligence will just kind of emerge. But a growing number of experts are saying, hold on, this whole brute force approach might be a trap, and it looks like we're starting to hit some very, very hard walls.
At the very heart of this problem is this concept called stochastic mimicry. Now, think of it like this. Today's large language models, they're brilliant impressionists. They've scanned trillions of words, and they are absolute masters at predicting the most statistically probable next word in any sentence. It looks like intelligence, it feels like intelligence, but it's really more like a super advanced, glorified autocomplete than it is genuine understanding. It's a system that's just mimicking thought without having a mind.
And here's a key flaw in that design. These models are totally static. Their knowledge is basically frozen in time at the very moment their training ends. You and I, we have a conversation, we learn something new, and we remember it forever. An LLM can't do that. To learn something new, it has to be completely retrained from scratch. This means that when they hallucinate, when they just make stuff up, that's not some bug we can just patch. It's a core feature of a system that's built on probability, not on truth.
And this table just brilliantly illustrates the two huge architectural pieces that are missing from today's AI. First, there's online planning. That's the ability to change your strategy on the fly when something totally unexpected happens. Second, and this is a big one, a world model, a real internal understanding of cause and effect. An LLM can predict the word shatter will follow the glass falls, but it doesn't understand gravity or fragility. It's just predicting text. It's not simulating reality.
And beyond these really deep software limits, the whole scaling approach is running into some hard physical barriers. You just can't keep throwing more and more data and more compute at the problem forever. The real world is starting to push back in two really critical ways: data and energy.
I mean, just look at this comparison. It is absolutely staggering. The human brain, the most complex object in the known universe, runs on about 20 watts of power. That's a dim light bulb. Meanwhile, training and running a single large AI model can require a data center that's guzzling milliwatts of power. We're talking the equivalent of a small city. This is just not a sustainable path to building intelligence. So to wrap this section up, the bigger is better idea is hitting a wall, not just because the architecture is flawed, but because it's becoming physically impossible.
Okay, so if just scaling up is basically a dead end, what's the alternative? Well, this brings us to a completely different way of thinking, something called cognitive AI.
Instead of trying to brute force intelligence by showing a machine the entire internet, this approach tries to engineer the fundamental principles of a mind from the inside out.
This timeline really puts it all into perspective. The first wave of AI, back in the day, was all about systems with hand-coded rules. The second wave, which is where we are right now, is about systems that learn from statistical patterns in huge amounts of data. The third wave, well, that's the goal. We're talking about systems that can do both, perceive the world like a neural net, but also reason about it logically and actually explain their thinking.
So instead of just looking for correlations in text, this whole approach is about engineering the actual components of a mind. Where an LLM is static, this is aiming for metacognition, the AI actually knowing what it doesn't know. And where an LLM is passive, this aims for goals, letting the AI act with purpose instead of just sitting there waiting for the next prompt. The crucial point here is that this third wave isn't about more data. It's about a smarter, more brain-like design from the ground up.
And this leads us to a really radical, kind of mind-bending shift in thinking. The idea is, if you want to build a true general intelligence, you don't train it on the entire internet all at once. You raise it. You teach it step by step, almost like you would a child.
And this isn't just some vague philosophy either. Researchers have actually laid out a tangible, step-by-step engineering plan. It starts with a real theory of intelligence, moves to building a core proto-AGI engine, and then proves it works in the real world. Only then does the raising part begin, with a whole curriculum designed to take the system from a basic learner to what they're calling a graduate-level intelligence.
So the crucial point is that this method needs way, way less data. It's a complete shift from brute force training to something they call Einstein learning, which is the ability to generalize from core concepts. Right? A child doesn't need to see a million pictures of a cat to understand what a cat is. They get the concept. This approach aims to give an AI that same powerful ability. The whole idea is to shift from mass training a static model to carefully cultivating a dynamic one.
So what does all this mean for the future of AGI? Well, it means the path forward probably isn't one approach versus the other. It's not scaling versus cognition. The future is most likely about convergence, about combining the very best of all of these ideas, from the software all the way down to the actual silicon chips.
A huge piece of this puzzle is the hardware itself. Today's computer chips, they have separate areas for thinking and for remembering, and they waste a ton of energy to shuttling data back and forth between them. The future is in what are called neuromorphic processors. These are chips that are fundamentally designed to work more like our own brains, merging memory and processing to be unbelievably efficient. So the grand synthesis, the most likely path to AGI, probably looks something like this: a hybrid system. It'll use the incredible language skills of LLMs as a kind of user interface, but that interface will be powered by a true cognitive core that can actually reason and plan. And this whole software stack will run on new, hyper-efficient neuromorphic hardware, all developed through that gradual curriculum-based approach we talked about. So, the big question, when? Well, given the immense challenges across all of this, software, hardware, this whole new developmental methodology, many experts now believe this convergent form of AGI isn't just around the corner. The consensus is really starting to form that a true human-level AGI will most likely arrive sometime in the 2030s. And this leaves us with a final, and honestly, maybe the most profound thought of all. If the path to AGI is less about programming a machine and more about raising a mind, it forces us to ask a much, much deeper question. It's no longer just about what we want our AI to know, it's about who we want it to become. And that is a challenge for all of us to think about.